I think right now where I am with this is I'm in the limbo between having a theoretical view of things that seems to have most of the big questions settled, and then trying to take that and get down to implementation. And I'm also trying to go out and talk about this so that I can figure out how to present these ideas and to make sure I've thought things through well. So that's another caveat, another reason why I would appreciate the feedback you have as soon as you have it. And part of what has informed me has been a sense of how software developed in the historical and cultural context that it did develop. So that's one of the tangents that we're going to go off on and that I'm going to try to use to frame the ideas. So I'm going to start with that and then talk about the key aspects of what the design of this system might be. And it has a lot to do with searching in terms of incomplete information and compressing the search space. And there are two major aspects to that. One is compressing joint relationships, and the other is compressing sequences that are made out of symbols that refer to these joint relationships. And then I want to talk a little bit about a tentative implementation strategy for this, and then go on and speculate about how it might be especially useful relative to what we have. So I think the main thing that has weighed on my mind and motivated me to want to get situated with respect to these ideas and figure out what's going on is that there have been a lot more hopes about what software could do than what software actually does. And I grew up in the early internet that was informed by a lot of computer lib type thinking, and I was always, expecting bicycles for the mind, and there'll be a lot more colorful metaphors for what we actually got later. And an interesting aside here that I didn't really know where else to stick in, but I think I'll just stick it in at the beginning and let it simmer as things go on, is that I discovered Carl Hewitt's career trajectory, and I noted that a lot of all of the themes that he worked on, first a planning-oriented programming language, and then the actor model, and now his latest work on inconsistency, robustness, and logics that can express uncertainty, all of those ended up coming up in what I was doing, even though I approached it from what seemed to be a completely different angle. So I'll just quote and refer to two of the great ones to frame this. Here is an important way of expressing, I think, where we are right now. So software means algorithms to us right now, and I got this out of something that was intended as an introductory textbook that was called Introduction to Algorithmic Thinking by Dr. Wayne Brown, and it looked like an interesting, well-written textbook. And I found that there was this pretty eloquent way of describing the state of the art in it and motivating why students would want to learn this. So he says, an algorithm is a precise step-by-step set of instructions for solving a task. And we we want to use computers, however, they currently have no real understanding or cognition. They can only perform tasks that people have developed algorithms to solve. So that's what you got to do. And maybe that is an unnecessarily anthropomorphic way of describing the capabilities that are lacking, but there is something lacking in terms of the computers being able to figure out what to do on their own. And what we're left with is algorithms, where we specify everything with absolute precision and determine exactly what's going to be done. Wait a minute. Yes, okay. So I had a bad moment a couple hours ago where my keyboard started generating inputs I didn't want to, and it started scrambling my slides, and I'm very paranoid about whether I got the slides I want. So anyway, so here is, I think, the revolution we deserved, and it was this agenda that was growing up in the 70s, and it became not quite in full form, not quite in a form that ended up working out, but it became this fifth generation computation agenda. And Robert Kowalski was I don't know, maybe one of the main, if not the main, thinker in this area of trying to use logic programming as a foundation for software. And he came up with this way of describing where we were going relative to where we were, that said an algorithm is logic plus control. So I think he probably meant exactly, like classical logic programming, because he was a logic programming guy, but I want to say that the logic of a situation is essentially the specification of how it behaves, and it doesn't necessarily use the formalism of logic exactly, but there's still this structure of the situation, and then and that is represented as a system of mutually related or mutually constraining quantities, let's say, or information would be probably better, given where we're headed. And then the control is this sequence of inference steps that you make within this structure to take the information that you have and work out what its implications are for the rest of the structure. And I would like to use a whiteboard, but I don't know how well that will work right now. So, oh, okay. And I actually want to embellish this as I go on and refer back to it. So.
I haven't heard anyone talk about fifth generation programming in a long time. So.
Yeah, well, I found that I was reading someone's reminiscences about how all of that went, and they were personally involved in some of the committees that were working on this, and they were talking about how the international politics of it worked out, and how like people were afraid the Japanese were going to beat them, and all of these aspects of how it became something that was very different from what it could have been, and it became this like political bone of contention that didn't produce any useful technical work, and it was this huge embarrassment to everyone involved in the end. And I guess that's a pretty common story in AI, where I guess there isn't a lot of constraint from people actually knowing what they should be doing, so other things seem to dominate how the discourse develops. And there's like people didn't like neural networks for 10 or 20 years because supposedly they couldn't do exclusive OR, and then someone makes this very small modification to let them do it, and now everyone does it again, and like kind of taking very little cues and blowing them out of proportion, I think. So yeah, I wish I could remember what that was called, but that's if you're if you like the strange, perverse history of how software research has gone, that's a good story to dig into. Oh, there it is. Okay, so. All right. No. Establish the drawing that will be embellished later. So here's just a bubble with things that might be connected in some way, and here's another one, and there's more, and then here's a third one, and these aren't connected, but these are connected to these somehow, and there's some kind of weird indefinite form of connection here, and then these can connect to these. So these are bits of information that are mutually related to one another, and this is how I'm going to try to draw the idea that there could be an indefinite sequence of relationships that represents a recursive form of relation that could be expanded in an arbitrary way. And this is going to be special because it's the query, so it's the ones that you want to get information about explicitly. And then these are only useful because they connect the facts to the query. So that's the basic picture. And this is basically Prolog, which is that you have your fact database, and then you have these things that you can recursively expand, and then you have your query.
So that middle bubble is like logic or rules?
Yeah. What should I call those? Well, I want to call them relationships because I want to say it's not logic. It could be something that is based in another information theory other than Boolean logic. So, and I think recursion is the main idea there, but this is something where I want to find a word that I haven't found yet, so if anyone has suggestions, that would be awesome.
Constraints?
Kind of constraints, but all the constraint solvers are also, they're basically on like the set theory level. So everyone has like stolen all the good words, and I don't know what the good one is that's left that I need to steal before someone else steals it. So let's call them, I want to call them relationships. So I want to call them recursive relationships. Maybe recursive relationships. Yeah. Yeah. Well, because then people are going to think like relational algebra and yeah. So no, that's not. Maybe it is. Well, because you don't have to do too much work to see where Prolog and SQL intersect, because there's that direct lineage right there. But I'm just going to leave that there for now.
So to summarize, you got a query, you got facts, and you got something in between.
Yeah, which is, and just if you know Prolog, just think like Prolog. Think this thing that has other things that I can also expand and blah, blah, blah. And there could be, there could be an indefinite amount of recursion in there, or it could just be something that bottoms out. But it's like, if you know Prolog, I basically want it to think of like making changes to Prolog as I go on with things. And I'm going to say this is like, this is Kowalski's picture. So and this is basically what Prolog ended up doing with just Boolean set membership. So if you have Prolog, then your query is just this like top-level recursive thing, and it can be, everything that appears in it can be recursively expanded into something that eventually refers directly to something at the fact level, and then it'll go and try to plug the facts in and then generate the solution set, and it's going to do it in this like left to right depth first search evaluation order, and that's what it's going to do. But
Are you talking about like mini-conrad or something?
Well, so yeah, there's a lot of Prolog-like things, but that is most of the ones I've looked at. But if you know of one, I mean, like if you go over to a constraint solver, then it's going to do something completely different with something that looks the same. But so anyway, I only mention it to tell you to try to abstract over it. So, but also to make things more concrete if that looks weird and you don't know what I'm trying to talk about there. Okay, and so we have this whole graph of relationships of indefinite extent because there's recursion involved. So that middle part and that dotted line means that could be arbitrarily large, potentially. So, and that is something that's one of the things that you have to work around if you're in Prolog. And the other thing is just that there are tons of paths, and if you're looking for an exact answer to your query, then you can't really neglect any of them that might be at all significant. But there is an intriguing empirical observation that comes from not logic programming, but he's just looking at a normal algorithmic software. But it's also, a very mature large package that has a lot of these paths that information might propagate around mapped out in it. So these are big mature software packages that have been in use and development for a long time. Hey, no problem. So let's say that because the army of slaves has been working on it for a long time, that it's gotten most of the space mapped out by hand, because that's what all of those people have been up to for so long. So it's gonna approximate like most of that graph in the middle with the structure that it embodies. What Menzies found in the paper that is, the name's in the heading there, the strangest thing about software is that there are a few paths that are empirically very thoroughly trafficked and are part of most of the evaluation that happens, and that's where you get the most benefit out of testing, and then there's this long tail of all of the other crazy paths that you could take, and then eventually if you have to work them all out manually, then eventually there are going to be paths that you didn't consider. If you have a way to do it automatically, then there's no path that you cannot deal with in theory, but if you have some way of like learning about the paths that you're on frequently, then it might be more expensive to deal with them or something like that. But what we have is that there's a lot of regularity in the paths that are taken, but and you can exploit that, but it doesn't give you a comprehensive picture of what needs to happen if you have a certain set of relationships that you're trying to model or enforce in how your system behaves. So if there might be a hope that we can make like a system for executing these specifications that can run with similar complexity to what we have if it can find these paths and do the same thing that we do by hand with them, and just have a backup of a general way to deal with the rest. And then it might not be more expensive to run, but it would probably be a lot less complex to write, because we'd just be writing the specification and then feeding it data so that it can find the significant paths. And I think that is like the one way of seeing that this might be practical and that we might be able to do this. But here's what we got instead. So as logic programming was quickly falling out of favor because it was was stuck with this problem of enumerating these combinatorially exploding search spaces, we got object orientation is one of the main things we got. So with reference to Kowalski's picture, object orientation, and there are a lot of things that have the same effect on the relationships that object orientation does, which is to, and such as modules and APIs, which is to draw boundaries around some of these relationships and to limit the paths that cross the boundaries to few of them, and to maintain most of them within smaller groupings. And so this came out of Simula, which was aimed at agent-based simulation of things, and there's a pretty clear domain-specific reason why things should be like this, which is that your agents have a lot of internal structure and they are only interacting with the world in limited ways. But then this was, viewed in these terms. This is a way to limit the paths that you need to consider through the space of recursive relationships. And I got a juicy quote from Fare, who was talking about microkernels, which is again a similar idea of having a kernel that is built out of lots of small modules. And I think nowadays we have the microservices, which is a combination of this with APIs. And so it was kind of a parody of what might be wrong with this, which is that you could chop up a big steak and wrap everything in little plastic bags and then tie it together in certain ways, but you've just kind of added a bunch of plastic and string to what you had there before. And fundamentally, whether you can find those boundaries depends on what kind of behavior you're trying to model. So I don't think it's, when you're doing agent-based simulations, then there's a good reason to think that you should be able to find that way of modeling things, but in other domains there might not be a good reason. So what I would like to suggest here is that the query is actually the way that you can accomplish what you wanted by defining an API, because it's a way to request information from another context. And then querying as driving evaluation is something that we're going to talk a lot more about. So the second thing that happened a little bit after object orientation, I think, came to prominence, but it was part of the same stew as logic programming, is functional programming with types, which is kind of why everyone signed up to this meetup group, I guess. And so that is, in terms of Kowalski's picture, that is where you're starting with, you're keeping track of this path, and you're keeping track of the derivation that you went through to build the thing you have. So you have this stratified type system, and it is probably constructive. And there might be equivalence classes of these paths, which is that you don't care about some parts of how something was built, but And then once you have something that was built up in a certain way, then you know where you can go with it from there. So that's useful and that's great, but it isn't grappling with what's going on in here at all. It's not addressing that, because here we have this big space of potential relationships that we need to navigate. So that's kind of dealing with an orthogonal concern to the one I want to focus on. So that I say just to situate what I'm trying to talk about relative to what is usually the subject around here. Okay, right, and great. So in all cases, we don't really, I had to draw this picture, I think, because we don't work in terms of this picture ever. We work in terms of the paths, and we describe how to take steps along these paths. So there's this implicit structure that we're trying to deal with, but it's never made explicit in the way we deal with it. So for that, I found it was apropos to quote whoever the author of stilldrinking.org is in his essay Programming Sucks, where he compared, he took a kind of dim view of the drudgery of programming, and he compared it to the opportunity to trim Satan's pubic hair while he dines out of his open skull, so a few bits of the internet will continue to work for a few more days. And I just couldn't leave that out, but that's how, and that's often how I feel. So why do we have this tangled mess of paths through a relationship graph that we deal directly with instead of just maybe we should learn to deal with this implicit structure that's behind everything? Well, why? I think why is always an interesting question, and it's hard to address without seeking all of the constraint you can. So the way of framing why that makes sense to me is in terms that are close to the technical background that I come from. When I was in school, I studied computer science, but I also studied control theory, and I specifically studied neural networks applied to control theory for nonlinear problems. So control theory is something that is descended from the intellectual ferment around cybernetics, which was mainly in the early half of the 20th century. And then I think as it focused more on the more mathematically tractable problems, it became control theory. But cybernetics was as much a philosophy as it was a technical field, and the term itself refers to the Greek term for the man at the rudder in the boat who's steering it as it's being pushed around by external forces and having it keep the course. And fundamental to it is this idea that there is information that is taken in from the environment, and the information from your environment plays a large part in determining the action that you're going to take. And there's feedback from the environment to the agent to the actions and back. And meanwhile, at the same time, there's a lot of industrialization is coming into its own the world over, and there's a lot of focus on mechanisms where you determine as much as possible a process a priori, and that by eliminating choices and degrees of freedom you can gain efficiency. And there's also some power in this, but these are radically opposed ways of trying to solve a problem, because one of them retains non-determinism as a reservoir of options that you can draw from in the ultimate situation you find yourself in, and the other one tries to eliminate degrees of freedom as much as possible to impose as much a priori structure as possible. And there's this, referring again to systems theory, I used the whole whiteboard now, didn't I? All right.
There are
Well,
erasers.
yeah.
There. Would you like to
Yes,
erase?
I would, there's a tissue right here. Someone threw an eraser, great. So there's this nice way of looking at that trade-off in that's an idea in systems theory that well there's two terms of art. One is the bow tie, and then I'll use this to illustrate the law of requisite variety. So here's my environment, and it's got a bunch of complexity. It can do all of these things that the agent might need to deal with. And then here are the actions that the agent can take, and then that's going to influence the environment, and this is our feedback loop. So the law of requisite variety is the idea that the agent needs enough internal complexity to be able to deal with, recognize everything that the environment could throw at it and come up with an appropriate action. And if there are if it is too restricted in complexity, then it's just like this counting argument type of idea that it's not going to be able to deal with some of the things it needs to deal with. So that's like this kind of heuristic way of thinking about the kinds of trade-offs that we're about to talk about. So, pardon me. So on the one hand, there's power in restricting degrees of freedom because you get efficiency and things become externally comprehensible. It's easy to tell how they're going to behave. But on the other hand, if you're really restricting how they can behave, then they might not be able to deal with what they need to deal with. They might not be able to do what they need to do. And so this is kind of a perennial, like fundamental, actual idea in political philosophy is the trade-off between freedom and rules, and are people inherently good or inherently bad. And one of the places where I think it really came to the fore in a form that is apropos is in legalism versus the 100 schools of thought. So in ancient China, there was this very diverse and rich system of many philosophies, approximately 100, maybe not literally, but quite a lot. And then the Qin Emperor unified China and instituted legalism, which was short-lived because it was a very harsh way of dealing with things. And the idea there was that no one should be able to know what the ruler's intentions are. So the only thing that the ruler is going to do is going to give people procedures to follow, and they will be judged solely based on whether they followed the procedures and not the results that they produced, or whether they actually anticipated what the ruler was trying to accomplish. So it's like enforcing procedural behavior on people who might be capable of goal-directed behavior. So I thought that was interesting. Yeah, right. So exactly. I mean, one of the things I want to show is that there's a lot of correlation of this with crazy tyrants who aren't really worried about accomplishing anything, or just worried about challenges from below taking away what they have. So, but whatever, that has nothing to do with programming languages. So, but it's fun. So, and then around the 19th century in America, you have, in the common law, there's a very, I mean, there still is, I think, there's a strong tradition of a substantive notion of justice where you're trying to produce a just outcome, but then but I think especially in the criminal law, it started to yield to this notion of procedural justice, where an outcome is just if it follows the right procedures, and what actually happens to the people involved is no longer of quite as much importance as it used to be. And that makes things easier to, makes things more deterministic, because you don't get into these debates about are we doing what we're supposed to be doing. You just say, well, there were 3 appeals and flip the switch. So, and at the same time, as part of this move towards industrialism that I mentioned, was that you had artisanal craft production yielding to factory production and Taylorism, where there were these minutely prescribed procedures that the factory workers had to follow, and they were supposedly worked out a priori to maximize efficiency, and that was like Taylorism. So, and this is a quite old distinction. It goes back to the ancient Greeks, where when they're talking about knowledge, they have episteme versus phronesis, and this is the one that is, well, so this is written before it because this is the framing. So there's this idea that Scott, an anthropologist, has called legibility, which is the capacity of something to be understood easily from the outside, and it's consistently something that empires are interested in creating in the territories and the people that they rule, but it doesn't just have to do with that. So the distinction here is episteme is the kind of knowledge that's easy to express in language and it's easy to understand in formal terms, whereas phronesis is the kind that isn't. And techne is the kind of practical capacity to act that is easy to express in language and formal terms and to understand theoretically, whereas metis is the other kind that isn't.
Is techne versus metis kind of like system 1 versus system 2?
Well, that's interesting. That's an interesting question. Because I think there is some overlap in that distinction. Because system 1 is you have this kind of formal, often linguistic cognition that you use to structure what you're doing in a top-down way, right? And then system 2 is, because in system 2 there's this idea that system 2 is like the reflex action, right? And something that might be misleading here is that
It's the other way around, but it
Yeah.
doesn't matter.
yeah. Oh, okay. Well, let's give them descriptive names, because I love it when people, like the philosophers do this too with time. There's like theory A and theory B. And it's like, well, which one is, and like one is relative to the speaker or something, and the other one is with reference to an objective coordinate system, something like that. But they certainly couldn't come up with descriptive names for those. So there's the system that is implicit and the system that's explicit, let's say that. And something like, I think that in the system 1, system 2 discourse, there's this idea that the implicit one is like reflex and it's less complex. But I think here there's actually a sense that the implicit one is much more complex, and that's part of why it defies being expressed in language and in simple terms. And that fits well with that picture, because there's so much more in the space of all possible recursive relationships than what we could ever represent explicitly at any given time. But anyway, what does this have to do with software? Well, I don't know, IBM was making census tabulating machines, and then a lot of the algorithms and data structures we have come directly from those kinds of efforts. Okay, another digression, because that's what this slide is about. So, in the military, at around the same time as well, there was, there's this long-running debate that runs up to the present between Auftragstaktik, which is basically what the German philosophy was in the Blitzkrieg, and everyone talks about the tanks, but actually a big part of why they were so efficient was that they gave a lot of autonomy to their lower level officers. And so they were just like, go blow up the factory, figure it out. And then, the opposite of that is someone who is imposing from the top the exact procedure, where they're like, okay, be at the hill at 9 o'clock and then rendezvous with the other people, at 11 and make sure you're not late. And the tactic is going to be minutely choreographed from above. So that was also something that was part of and of course IBM was making census tabulating machines, but a lot of computing was actually coming out of, military computers that were calculating ballistic trajectories. And this cybernetics versus mechanisms was there too, because while you had that going on, you also had things like thermostats and simple autopilots and stuff being developed so that you could aim. So one side was aim your weapon, and it's just like an artillery shell that can't navigate, and the other side was have your weapon aim itself. And by the 50s, you had the heat-seeking missile, and it had a way of tracking a big, bright infrared spot and turning to face it. So letting its behavior be controlled by information from the environment. So what do we have over in the software world? The cybernetics people didn't really win. They kind of became control theory, and they went off and solved a lot of very specialized problems. But the logicians came in, and they laid a lot of the theoretical foundations for computation that we are still thinking in terms of. And complexity theory became this kind of weird thing that you do at the Santa Fe Institute. And so on the one hand, we have type theory, which is what we're all used to talking about here, which is let's eliminate all the cycles, let's eliminate all the self-reference, make everything constructive, everything well-defined in that sense. And then complexity is what is all the rest of the stuff where you can have self-reference, and now you have to introduce like a time dimension to see how things evolve, and you have to quantify the degree of mutual influence so that you can make sense of that. And things, as the name suggests, become a lot more complex, but it also broadens the range of things that you can actually consider significantly. So now we're coming up to the 80s and fifth generation, so or what it might have been. So at the time we had, early neural networks were kind of coming back into fashion because that frivolous objection had been debunked, and there might have, sadly, so information theory, the main textbook on information theory didn't come out until 1991. So I wonder if the people who were working on this had even ever heard of quantifying information and stuff, because it's very electrical engineering, is very communication theory specific at the time. So that might be why things didn't quite work out. I don't know. And also we had PCs came on the scene, and they were like kind of pocket calculators attached to televisions, and they didn't they didn't have floating point units until like the mid 90s built in, and there wasn't a lot you could do with quantifying much of anything. So really they were just like these arithmetic and logic units, and they were very discrete, and they could kind of do math, but nothing remotely like what we have now and we're completely used to. So finally coming back to what was going on in actual programming languages. So Carl Hewitt was, I think this was the earliest major thing he worked on, but is that the case?
Sorry, what?
Planner.
Yeah.
That's like, I don't know, 73-ish, right?
That's about right.
Yeah, so that was this programming language where evaluation was planning, and it was great, but you had to enumerate these huge spaces. So then there was kind of a split into schemer and screamer, and screamer was kind of this Lisp where you bring a little bit of search back in, right? And schemer is what eventually becomes scheme, and that's where you just forget you ever cared about that for the most part until you get to the chapter 9 in the book about it or something. So, and then we have another interesting lineage, which is where so Prolog was at the root of another part of this tree, and a branch off of it was Icon, which introduced a lot of extra syntax and eliminated unification, which is unfortunate, and that was one of the distinctive features of Prolog. And then, but people have written it back in. And then Python came along, and it eliminated the generating solution sets from Icon as well. So now you just have this thing that's kind of like a lot of fancy macros for C and some nice standard libraries. So it kind of, along this lineage, we got all we kept was like a nice syntax, and then everything else got left behind. And now we've got all of these GPUs in our phones and stuff, and deep learning is interesting. So this is kind of a resurgence of the neural network stuff. So what might be interesting about it right now in the context of what I'm trying to talk about? Oops. Okay, we'll come back to that. Okay, so yeah, these that was part of the slide shuffling, I think. So let's come back to that later. So before fifth, there was fourth, Charles Moore's brainchild, which was actually also inspired by Lisp, but he just pared it down to basically one mechanism, which is there's a dictionary, and you have there's the base sequence of operations that the machine gives you, and then you have a dictionary where you can define longer sequences of them and refer to them by a single word, and that's it. That's like all of fourth. So what is this letting you do? People talk a lot about how amazingly concise it lets you make your programs, but why does it do that? Well, I would like to observe that this is actually exactly the same mechanism that you have for dictionary-based universal compression of sequences, and that is universal compression lets you achieve the information rate of whatever you are compressing. So that's actually quite a powerful tool, but it doesn't figure out how to compress the sequences for you. You, the programmer, have to figure out how to use that. You have to think about it, profile it, whatever you do. But if you're smart and you know how to do that, then you can do quite well with that mechanism. So, and these sequences of instructions that are executed are, with reference to that picture there, the paths through the relationship graph. And yeah, this is, you know, LZW works that way too. And I've read Chuck Moore's blog, and I've read a lot of his essays about what he's trying to do with software and his objections to software as it is now. And I couldn't find exactly where he said what I had in mind, but he said limit the scope of software. So keep the paths few and the query simple, and then the relationships remain manageable. And then this is the ideal tool for dealing with that, because you just have a few paths and you can deal with them. But sometimes we might not have that option. So how might we capitalize on this insight? Well, maybe we could take this more abstract version of what's happening and go with that and automate finding and compressing the common paths. All right. What was I trying to do here? Okay. Right. Okay. So back to the logicians and ripping on logicians. So we've seen with the bow tie that there's a kind of a harsh trade-off in knowing how something works versus having confidence that it's going to do something that you want it to do. Here's another way to state that. But there is in the culture that I think we're in this idea that it's good to make radically simplifying assumptions and just go with them, and that's the unreasonable effectiveness of mathematics. But then the complexity theorists have the opposite slogan, which is the unreasonable ineffectiveness of mathematics. And a lot of this starts with physics, I think, and as far as I can tell, because you kind of have, you have Newton, and then you have statistical physics, and they're both making, they're finding these relationships that seem to hold really universally, and they're making assumptions about how things can, like assume all of the particles of the same species in the box in the ideal gas are the same, and they're in a box, so they're perfectly isolated, and assume they're in equilibrium, and so on. And then if you try to model the situation linearly, you get the ideal gas law, and so on. So. And that's really great when what you're looking at actually has the forms of regularities that you posit to them. And the way you find out is you can posit it, and then you can see if it leads you anywhere useful. And then when it comes time to apply it, so you've recognized these relationships, you've tested them, and then you bear them in mind, you try to use them to work out something in a new situation where you have a new question to ask, and you just assume that the structure of mutual relationships is the same as what you've seen elsewhere. But as the 20th century wore on, then, and engineering came to be more, I mean, that was really the 19th century, but 19th and 20th century, depending on the field of engineering, but things get more and more practical as they develop the sophistication to relax these assumptions. So, you know, once you start to be able to add friction and wind resistance and stuff, then you can like make a car, but until then, your car is gonna be weird and it's gonna look like a box or something, but some of them still do. So, and economics is a nice example of how you just try to make the same assumptions that they made in this other situation that was a lot simpler and just go with it, and then you get a disaster that is criticized very effectively by this guy who used to be the Greek finance minister until lately, and Steve Keen at Kingston University also has a lot of good descriptions of that. He's actually developing dynamical systems models that are a lot more like the system theory stuff, but that's, so I think that's an example of how this is like clearly a mistake, and I think software is making the same kind of mistake because it's trying to like impose these arbitrary restrictions on the kinds of relationships, and instead of like going for generality first and then, you know, optimizing the common cases. And like, I should stick Perlis in here, who said that premature optimization is the root of all evil. I think it's probably Perlis. He's the aphorism guy. Yeah, so it's all premature optimization right now. Okay, but man, that really doesn't belong there. Okay, we basically said all that. Great. Let's do this. Okay. So this is a slide I borrowed from a talk last month that was actually about statistics as well, but just kind of ignore that. So here are the two things that are really apropos to making the system work, because they're going in the direction of progress that I've defined here. So on the deep learning side, we have this interesting new set of capabilities that we're developing, which they can find patterns of joint variation from the data, and they don't really have like a clear theory of information in how they represent the data and what they've learned from it, but it's kind of like a fuzzy-like representation, and sometimes you'll take that and normalize it at the end and get a probability distribution or something. We can recursively compose these things so we can get it multi-scale structure, at least across space. And that was inspired by theoretical neuroscience, where they did the experiments on the cats where they looked at the low levels of the visual system, and then they presented these idealized like edges and lines and little atomic bits of contrast, and then they saw which neurons fired, and then they went a little further up in the visual system, and then they found that, you know, like shapes were being recognized and were causing these things to fire, and then presumably that goes on, and some people have posited the Jennifer Aniston cell or whatever, but maybe it doesn't quite work that way. But it does seem like there's a more and larger scales are being covered as you recursively build up these data-driven representations of the joint variation you've observed. And now there are these kind of early efforts to do similar things and to use those to solve problems. And on the like AI that you would call by the name AI side, there's recursion, and when we want to deal with those directly, we use grammars, which are basically composition rules, and for the most part, everything is Boolean logic. Not that people haven't tried other things, but that's still where most of the work lies. And we're really good with process here because we can have like a recursive way that something at time t can be related to something at time t+1. So that's something that's easy to do on the computer science side. But we're mainly dealing with like discrete variation here, and we don't have this kind of continuous partial representation of information from over here.
Can I ask you a question?
Yeah.
At the risk of sounding kind of stupid, I don't understand your thesis. Like, I don't. What are you
Oh, yeah.
proposing we do with software? Like,
Um,
in what way should it change? Like, in a way where I'll be able to understand.
Yeah. So I think what it's getting to is there are now ways of searching spaces that deal with approximate information instead of exact information, and those are quite efficient. And we can revisit these old agendas of having like a search-driven, planning-driven evaluation, and then we can deal directly in terms of the specification of the relationships. So that's like where this is headed, but then there's all of this window dressing about like how and why one might do that, because it's been considered impossible or folly for a long time, and the 5th generation thing running aground was a big part of that. And
To simply simplify, I think Anthony's agenda is basically SQL for general purpose computation.
yeah, I think that might be the best slogan for it, but as you are noticing now, I'm still figuring out what I should be saying and how I should be presenting it. So, okay, so yeah, we basically said that. So that, you know, these things do recursion with partial information, so that could be quite useful. So here are 2 main strands of thought in deep learning. One is the auto-associator, which is this thing I was talking about before, which is it's a thing that has a little bit of hidden state, and it learns a map into and out of that hidden state that can represent whatever the variation is in the base representation that it's looking at. So in the visual system, it's, you know, taking a bunch of retinal cells and figuring out that like lines and edges are significant there, and so on, you could say. And how much that holds biologically is a very open question, but at least this is an idea we could go with maybe. And some of the ways of doing this that people have come up with on the computational side make fairly heavy assumptions about what they're trying to model, but that's not the only way to do it. Some of them are just working in terms of information theory, and they don't really care what the distribution of what they're looking at is. And I've mentioned that there are really good approximate search techniques, so for now, I think this is a big blind spot in the deep learning field, which is they're trying to do gradient descent for everything, including very non-convex problems. But you don't have to do that. You could build one of these out of, you know, using some kind of good search to fit it. But so there's another strand of thought here, which is the work on recurrent nets, and that is trying to grapple more directly with this idea of, can we do recursion, can we do general purpose computation in this framework? And just over the past year, there have been some really interesting developments, the neural Turing machine and the reinforcement learning neural Turing machine. Prior to that, about 10 years ago, there was the LSTM, which it basically has a bit of fuzzy state in it and has a little feedback loop in it that you can kind of multiply by a constant that depends on the input. And the authors of the series of papers that introduced this said that the important thing was feeding the error gradients back in time, because they really like to use gradient descent on non-convex problems. But something else it does is it feeds the state forward in time, so it gives you a little bit of fuzzy state that you didn't necessarily have before. And then these neural Turing machine things, they're basically just looking at a Turing machine, and they're taking everything that's discrete about it and introducing a parameter that interpolates between the 0 and the 1 and the bit that describes it, and they're trying to do gradient descent again. But then reinforcement learning neural